Okay, so this video we're going to look at the internals of the gkv4. So the device is here, it's powered off, we need a couple of tools to access. So the initial access is via some screws on either side, as well as some on the back. So we're going to take all of those out now. Right, then that's all those screws out, and you see now the back is fairly loose. Now I'm just going to tilt it off rather than anything else, just to keep the bits all nice and secure. So you can see here now two parts. These are the buttons, 3D printed buttons for the bumper buttons, so we'll put those somewhere safe. And now the trigger is visible on this side here, on the left side. So these are actually on a pivot. And the idea is there to make it a bit more natural, so you can either push them in or you can sort of pull on them and it still has the same effect to cause the button to be pressed. Put that to the side and have a look at the device itself on the right. So the device is in several circuit boards. There's the main board here at the top, the control board at the bottom. The control board has a slight riser as well, and that was actually necessary to get the trigger buttons just up to the appropriate height, because they rotate, they don't press directly downwards. The height above the board is very important for where they sit. There's the inbuilt speaker here which connects up to the main board here, and a couple of cables going around to the front as well. So we can see here two cables going to the inbuilt battery. There's a temperature sensor and also the power itself. And you can see the various controls. So the controls are pretty standard PCB contacts, and they have these rubber connectors, and these are taken from a repair kit for an Xbox controller. So let's start taking the board apart, and we can sort of have a look and see what's what inside it. So the first thing is to separate the two boards. Now the two boards are separate. The main reason is for height reasons. So the controls, it's very important to get these thumbsticks in exactly the right position related to the screen, and if they're on the same level as the main board, then they'll be sunken back too far and the ergonomics would not be good. So let's separate these now. You'll notice that for space reasons the battery backup is here, so when I disconnect this I'm actually going to lose the RTC, the real-time clock settings, but luckily it reprograms itself from internet time, so it'll be absolutely fine. So let's disconnect now the back, and then we take off the main board first. Use our trusty spanner to the appropriate size. The main board itself is held in by these adapters here, which connect to the control board, which I'll show you in a second. By the main screws itself, which hold the back of the case in, and the case also has lots of various studs aligned to touch the flat parts of the board to keep it all nice and together. Now I've glued in the screen a little bit, so this may be a little bit tricky to get out, but this all comes out as one block, one big assembly. So let's lift it up there, and we'll take it out as one big assembly. There we go. Doing our best to tilt it, so some of the buttons fallen out. This is standard for the device. So these are the power and volume buttons. Let's put those somewhere safe as well so we don't lose them. Right, putting the control board to the side for the moment. We'll come on to that later. We come to the main board itself. Now I'm holding the screen together. I'll show you the other side in a second, but as you can see, it's got this is the back side of the board, so a few of the controls. This is the UART connection going around and coming out on the front, and it's a 6-layer board, but it's got components on both sides, so you can see just through the Kapton tape there's the MO402 capacitors underneath the main chip itself. You possibly can't see, but underneath on this side there's some more underneath the DDR RAM and a few other bits and pieces. This is the volume, this is the throttle control, sorry, but it is the repurposed volume control from sort of CD Walkmans and so on. There's a couple of buttons, so one of the buttons is the reset button, accessible from outside the device. This is the programming header, and this is a button that connects to one of the boot pins on the STM32. And what this allows is it allows us to adjust where the device boots from, and the standard is to boot from the onboard flash. If I press that and hold it down during boot, I can put it into development mode. And another couple of buttons here, so these are the bumper buttons. Right, let's turn it over and have a look at the interesting side. So there's standard switches for the volume, for the power, for the USB, and that's the headphone jack. So this is the screen itself. The screen sits on a support, which is 3D printed again, and inside the screen support is the battery itself, and this is a 10,000 milliamp hour battery, and we'll take all that off on block in a second to demonstrate the rest. So let's put that back for now, flip it over and take off that battery support, the battery holder, which is available as an STL file in the repository. On there, and somewhere under here, I can just flip up this tape. I'll be able to get to the other one. There it is. And now the battery and the screen should be free. So let's flip the screen back down, and then this all comes off, and this sits nicely in a little area there, and then we can expose the entire board itself. Okay, so now let's talk about some of the components on the board. So we already mentioned in the middle here we have the microcontroller itself, the STM32MP2. Coupled to it is 1 GB of LPDDR4 RAM. So let's talk about everything else surrounding that. So starting from the top, let's talk through the power path. So this is the USB-C header, where both power and data comes into the device. There is a TVS, a transit voltage suppressor diode on the bus and on the data lines, and then this all feeds through to a battery charger, and there's options for two different types of battery charger. This is the version 2 in the schematic. It has a slightly higher rate of charge, which is beneficial for the higher capacity battery in this device, but there's also place for the old one there. And the power comes down this main wide PCB routing here into the power management IC device itself. Now, STM provide a particular chip that's supposed to be paired with the controller called the STPMIC25, which is what is sat inside the middle of this board. Now this is a separate 4-layer board that I created for the gkv4. The reason essentially is one of pragmatism and to facilitate rapid prototyping. So as you can see, there's an awful lot of capacitors and inductors that are required to support the PMIC IC. But every time I was redoing the rest of the board, I would have to resolder all of these, and to create the boards I do manual pick and place with tweezers and suction devices, and then Fluser PCB oven. So it took a very long time to do the pick and place for all of these because they're all slightly different values, etc. So to facilitate rapid assembly, I got these small 1-inch square boards made and panelised, so 6 of them produced at a single time, then just literally created a lot of these. So I had a known goods supply that I could then just attach to the main board, and this attaches through sort of castellated holes, LGA pins on either side. And this outputs a number of voltage rails, all of which can be tested on the various test points dotted around the board. So I'd say that connects to the CPU and to the memory. There's also down here the SD card, which we'll talk through. So this contains the user space applications to load it up, and it has the usual sort of high-speed data bus connecting it to the device. Down here we have a level converter. So in this particular setup, the majority of the I/O ports from the device are 1.8 volts, and the screen here requires 3.3 volts on all of its RGB data lines. So this is a 32-bit level converter which handles all that for us, and it's very close proximity to the ribbon cable going out to the screen. On this side we've got the ribbon cable attachment for the capacitive touchscreen IC, which is embedded into the screen itself. If I flip the screen over now, we can see under here we have the boost converter for the LCD backlight, and that's all in the circuitry here. Down here we have the tilt sensor, and the tilt sensor chip itself is here, and actually as it sits within the case, this is the dead center of the board. So as you can rotate the case, the case around its center point, and it will get accurate tilt rotation. So this is a combination accelerometer and gyrometer. There's also pads for a magnetometer and LIS2MDL, but when I built this board I did not have one available, and there weren't actually any in stock at the usual suppliers, so I skipped it for this iteration, but it's there if one becomes available in future. And there's a high side voltage switch here. It means I can switch off these components for games that don't require them, and thus save power. Coming around to the bottom right of the board, we have the Infineon Wi-Fi and Bluetooth chip. This is on, I think it's Embedded Artists M2E board, which I just got because, again, for ease of prototyping, it means I didn't have to waste one every single time I went through a new iteration. I could just take this module and put it into a new board, and it's attached through an M2E header here. Coming up this side, we've got the voltage up and down and the power buttons, and they've got pull-ups as well as RC filters attached to each one. In the top here we've got an unpopulated section, and this is filters through to this unpopulated section here. So this is a USB-A host port, again with a TVS attached to it. And this over here is the boost converter for it, so to create a 5-volt USB V-bus. I simply haven't found a use case for this, so this is unpopulated, but should a reason to have a USB host become available in future, then it's there, can be added on, and it's already connected up to the chip through a sort of a USB 2 interface. Then in the top left of the board we've got the ADC for power, for the audio, sorry. So this is the DAC, so this is the DAC chip itself, sort of 24-bit I2S adapter, and it connects, it's got its capacitors and resistor network around it, and it connects directly to the headphone output, so it's got an inbuilt headphone amplifier. Now this is a switched socket, which means that if nothing's attached it bypasses, and it bypasses back down this route here, and that's then converts stereo into mono, just as a pass-through to two resistors and combined together, and that goes into a Class D audio amplifier, which connects to the inbuilt speaker. So if the headphones are attached, the speaker disconnects, and if they are not attached, the sound goes directly to the speaker. Any other thing to mention is here we've got a 20 pin trace port for the device, so if necessary, if high-speed hardware trace is required, I could put a header on there and I could trace it, but I have not yet found a use case for that either. And then finally down the middle of the board we've got two oscillators, so there's a 40 megahertz crystal here, and then there's the standard RTC 32.768 kilohertz crystal just below it, and that provides real-time clock for the device. Now finally we're going to talk about the control board. So this is the inside of the case as before. The control board has all the controls on the front of it, and it has an adapter here to connect through to the main board. Some of the buttons are falling out, so let's just put those to the side. We'll find that later. Let's take this out now. So under here you can see the backs of all the buttons. Again, these are all 3D printed buttons. Pretty standard. The STLs are all available for the various different sizes. These are the start and select buttons, and they're all obviously adjusted to the appropriate height to fit against the buttons on the PCB. Now the menu button itself is slightly more complex. I don't know if you can see on the translucent resin, but it's got little notches because it has a decal on the front, and that fits into the notches here to prevent it rotating and to make sure the decal stays upright. And then the D-pad buttons are these guys here, and again all sort of 3D printed with a nice sort of smooth bit in the middle. There's that. So let's put that to the side. And finally let's look at the control board itself. So the control board is, let's take these out so something's loose. So the control board is this. So this has all the main controls on the bottom, and again it's on a separate board as mentioned before to allow different heights, but also so I can make this once or change it as necessary to add extra features and so on. So the control board consists basically of PCB pads with these rubber buttons, when these have contacts underneath them, so when they're depressed they combine, and there's interlocking mesh essentially of signal and ground, so when this is pressed down it links those together. And these come from a standard Xbox controller repair kit, and indeed the menu button with the LEDs is very, very similar to what we would find in an Xbox. The thumbsticks are again from the same repair kit and have the usual rubber pads on them. So other things to describe on here, the start and select buttons are just simple micro switches on the board, just because there was no need to have them be sort of very rapid pressed and nice soft presses. Down here we have a I/O expander, so there are simply not enough pins either in the connection header or actually in the CPU itself to allow me to connect all the various buttons, so they go into an I2C I/O expander here. There's some little attachments here for the riser board, and then on here we've got basically what is a glorified LED driver. So it's simply a ULM 2003, a Darlington array, which I just had a lot of, so I decided to use it to allow the RGB LEDs to be driven from the 1.8 volt output of the microcontroller. This is the one with the built-in gate resistors, so it was quite an elegant solution just to have it all in one chip. So there are 6 outputs in total, so there's red, green and blue for both of the different LEDs. So it's quite nice just to have it all in one chip, and they're very cheap, and I had a lot of them. So that is it really for the control board. Now I'm going to stop there. I'm going to try and get all this put back together.